Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, minimum substring partition of equal character frequency. We will also be discussing about one harder follow-up to this problem wherein s dot length is less than equals to 5000. So if you have already solved it and is here just for the follow-up, all the timestamps are there in the description down below. You can move to the section of your choice by skipping the rest of the video. With that, let's get started. The problem states that you are given a string s and you need to partition it into one or more balanced substrings. What is a balanced string? A balanced string is a string which contains where every character occurs the same number of times, right? Now, if you take an example, ABA BCC, one of the balanced partition is AB, AB, C and C. Why this is balanced? Because if you look at every substring, each of these substring is balanced, because in this case number of A is 2, number of B is 2, and hence they are equal. So this partition, this substring is a valid balanced string. Similarly, in this case, because there is just one character, so it is equals, like you don't need to equate it with anyone else. So this by definition is a balanced string. Similarly, this is again a balanced string. So every substring in this partition is a balanced string, and hence this entire partition is a balanced partition. Now your job is to return the minimum number of substrings that S can be partitioned into, right? So let's take an example. Let's say S is F, A, B, C, C, D, D, G. There are various possible ways to partition this S into a partition of balanced substrings, but among all such ways, these two ways have just 3 substrings in the final partition, and all other ways will have greater than 3 substrings. And as your job is to minimize the number of substrings, these two are the best one, and hence the answer here is 3. That is, at the minimum you can get a partition with 3 substrings, right? So hope the problem statement is clear. Now before solving the problem, let's try to understand whether it is always possible to partition the string into balanced substrings or not. Because if it is not possible, then problem doesn't talk about what to do. So ideally it should be possible, otherwise problem statement itself is kind of flawed. So think about it. We need to partition it into balanced substrings. So let's not worry about the minimum number of substrings. Let's just see what's the easiest way of selecting a substring which is balanced. So the answer is, you can just select one character, and if you select one character, frequency of every character in that one character string will be equal, and hence that string would be a balanced string. So what you can do, you can easily take one character at a time and form one substring with that one character, and you can partition this entire string into n number of substrings, where n is the number of characters in the original string. So even if you can't do anything else, that thing is something you can always do, and hence it is always possible to partition the string into substrings, into balanced substrings. And because of that only, the problem doesn't talk about what to do in case it is not possible, because it is always possible, right? So in worst case you will have an answer of n, but you can do better in most of the scenarios. So now let's think about how to solve the problem. So let's say this is the string you are trying to partition, and let's think about what's the first substring could be. So this is a valid first substring. right? Because we already discussed a substring with just one character is a valid substring. Now this is again a valid substring, right? Because frequency of A is 1, frequency of B is 1, and they are equal. So this is again a valid substring. This is another valid substring. Note that we are only considering the substrings which starts at 0 because we want to find out what are the different possible first substring, right? So let's say you figure out that okay, this is one of the first substring I will have. Like there are various possible ways, but let's say you fixed one possible way first, and then you will figure out what is the total number of substrings this rest of the string can be partitioned into, right? And then you can say okay, now I will try second possible way to partition the first substring into, and in this as well you will say what is the total number of partition I can partition the rest of the string into, right? So isn't the problem equal to the original problem you are solving? Originally you were saying that okay, what is the total number of partition or minimum number of partition in which I can partition this entire string. Now you are saying that okay, after fixing first partition, whatever string is remaining, tell me how many partition or what is the minimum number of partition in which I can partition this entire string. Is this problem is exactly equals to the original problem, just that original problem had a greater length string and this problem has a smaller length string, right? So hope you can see the recursion here. Because you are solving the exact same sub problem, you can actually write a recursive function to and call that function every time to solve the smaller problems, right? So let's look at a formal recursive function. So you have a function f, let's say, which takes in an array and will give you what is the minimum number of partition in which I can partition this entire string into, right? Now what you are saying is there are various possible ways to partition the first string, right? So in this particular scenario you can take a, right? You can take ab because this AB is again a valid first partition. Then you can take AB, this is a valid first partition as well. Then you can take this entire thing as well. This is again a valid first partition, ABA, BBA. So among all these valid partitions, what you will say, okay, after I take A as the first partition, now I need to know how many minimum number of partition I can partition the rest of the string into. So you can call this exact same function with everything starting at B, right? Or starting at the first character. Similarly, for when you choose AB as the first partition, what you want is how many minimum number of partition I can partition the remaining string into, right? So for that again you can call the same function with a reduced array, right? And similarly for this one and this one as well, you can call the exact same function with some reduced version of the array, right? Now based on what you are getting from here, let's say you are getting x1 from here, you are getting x2 from here, you are getting x3 from here, and you are getting x4 from here. Based on what you are getting, you will just take the minimum across all of them and that will be your answer. Basically this x1 denote that to partition the remaining string I need minimum x1 number of partition. So this was the string, right? So to partition this remaining string I need x1 number of or I can partition this remaining string into minimum x1 number of partition. Similarly this x2 denotes I can partition the remaining string. In this case the remaining string would be this particular string. So I can partition this remaining string into x2 number of partition, minimum x2 number of partitions, and similarly x3 and x4, right? Now what you wanted what is the minimum number of partition I can partition this entire string into. So what you can simply do, you can simply take the minimum across all of them. Let's say minimum is x3, so you will say x3 plus 1 is my answer. Why plus 1? Because you have already partitioned the first, you have already removed the first partition, so you have already done one partition before, right? So this is how this recursive function would proceed. So let's look at the recursion. Again, if you don't understand this, don't worry, the next section of the video we will be doing complete dry run of this particular solution, and I'm very sure you will be able to get it there. But before that, let's look at the pseudo code for this. Pseudo code would be exactly equals to what we just discussed. There will be a function which will take in an index. Now why index? Why not this entire array? Just think about it. What we are doing, we are simply saying that, okay, I will remove the first partition and then I will say what is the minimum number of partitions I can partition the rest of the string into. So the remaining string will always be a suffix of the original string, right? So why do you need to carry this entire array with you? Instead of carrying this entire array with you, you can simply say, I will maintain the starting index, and I know this, my remaining string would just be the suffix of would be everything starting from that index. So you are finding out f of 0, which means I want the minimum number of partitions for this entire string starting at index 0. Now once you consider this a as a partition, you want f of 1, which in turn means I want minimum number of partition to partition this string into. Now once you take ab, you want f of 2, I want minimum number of partition to partition this entire string into, right? And similarly for ab you need f of 4, and for this you need f of 6, right? And you will get the minimum across all of them and just do plus 1 to get the value of f of 0, right? So you can simply maintain an index I, which will simply denote what is the remaining string you want to partition into minimum number of partitions, right? So f of index denotes what is the minimum number of partition to partition the string starting at index I and b. Now if index is completely exhausted, there is nothing to partition, so you will simply return 0. Otherwise you will look at your dp array. Why this exists? Because we have to do memorization. If you don't understand this, just wait for the dry run and I'm very sure you will be able to get it. Now after that, this is the maximum answer that we can get. We already know that even if nothing is possible, we can still make one character as one substring and partition this entire string into number of substring which is equals to number of characters. So in worst case, this is something that is possible, that you know for sure. Now what you want is, you want to iterate over all possible first partition. So you will simply iterate over everything starting at index and go all the way up to n. Now you will keep maintaining the frequency of all the elements or all the characters you have seen so far starting at index up till I, and if frequency of all the characters are equal, it means whatever you have considered so far is a valid partition. So you will take that as a valid partition and partition the remaining string. So f of I plus 1 will denote what is the minimum number of partition to that the remaining string can be partitioned into, and you will simply do plus 1, that will denote what is the minimum number of partition to partition the entire string starting at index I and d, and you will take minimum across all those possible partitions, and answer will finally contain the minimum number of partitions which you can partition the entire string starting at index I and d. And finally you will store that in the index and return the in the dp array and return that, right? So this is how you will proceed. Now if you don't understand this, I will be doing a dry run just after this. If you already understand this, feel free to skip the dry run and move to the next section of the video where we discuss the time complexity of this entire approach and the code as well. So next we will be doing a dry run. Let's assume that it's the same array and you wanted to figure out what is the minimum number of partition you can partition this entire string into. Now, as we discussed, f of I denotes what is the minimum number of partition to partition the string starting at index I. So you wanted to partition this entire string. So what you want is the value of f of 0, which means what is the minimum number of partitions to partition the entire string starting at index 0, right? So we want f of 0. Now what is the approach? Approach is, let's first fix the first partition. Now what are the valid first partition? This is one possible valid first partition because the frequency of every character is equal. So if this is a valid first partition, what you want is what is the minimum number of partition to partition this entire string into, which is string starting at index 1. So you want f of 1. Now if f of 1 is x, then one possible value of f of 0 would be x plus 1, right? That's how it will go. Now second possible valid partition is AB, because the frequency of A is 1, frequency of B is 1, and they are equal. So you want what is the minimum number of partition to partition the string starting at index 2. So you want f of 2. Similarly, one other possible valid partition would be AB, frequency of A is 2, frequency of B is also 2. So you want the number of smallest number of partition to partition the entire string starting at index 4. And finally, one more possible valid first partition could be this, in which frequency of A is 3 and frequency of B is also 3. So you want the minimum number of partition to partition the string starting at index 6, that is f of 6, right? Now you will expand f of 1, right? So to figure out the value of f of 1, first of all, what f1 denotes? F1 denotes that what is the minimum number of partition to partition the string starting at index 1. So you are currently looking at this entire string, right? Now approach will be exactly same. You will just figure out the first partition. So first valid partition is, one possible first valid partition would be this B itself. In that case, what you want, what is the minimum number of partition that we can partition the remaining string into, that is f of 2. Another possible valid first partition would be 1 and 2. In this case, you will again want what is the minimum number of partition to partition the entire string starting at index 3. Now there are no other valid first partition, so these are the two valid first partitions. So we just have to calculate f of 2 and f of 3. Let's say it is x, let's say it is y. So the value of f of 1 would be minimum of x comma y plus 1, right? So now we'll calculate f of 2. Again, f of 2 will be calculated in the exact same fashion. F of 2 denotes that what is the minimum number of partition to partition the entire string starting at index 2. So again, you will first figure out the valid first partition. This can be valid first partition. So you want the number of minimum partition for the remaining string, which is f of 3. This can be another valid first partition. You want the minimum number of partitions starting at index 4. In this case, this can be another valid first partition. You want the minimum number of partition starting at index 6. And finally, this can be another valid first partition, and you, in this case, you want number of valid partitions starting at index 8, which is f of 8. Now in the similar fashion, you will keep on continuing for f of 3, f of 4, f of 6, and so on and so forth. For this example, let's continue exploring f of 8 because these all will go in much greater depth. So let's say we want to find out f of 8, which means number of partition to partition the entire string starting at index 8, which is this string itself. Now again, the approach would be exactly similar. You will simply figure out what is the valid first partition starting at index 8. So this can be a valid first partition. So you will say what is the minimum number of partition to partition the remaining string into, which is starting at index 9. Similarly, another possible valid first partition could be this, because the frequency of D is 1, frequency of C is also 1, so frequency is equal. So in this case, you want what is the minimum number of partition to partition the rest of the string, which is starting at index 10. So this value would be 0 because there is no string at all. So this value would be 0. So one possible value of f of 8 would be 1. Now in the same fashion, f of 9 would be at least 1, right? So another possible value of f of 8 would be 2. So you will simply take the minimum across 1 and 2, and minimum would be 1. So f of 8 would simply be 1, right? Now you will return f of 8 as 1 here. So one possible value of f of 2 would be 2, 1 plus 1. And similarly, you will get another values from here. You will take the minimum across all of them, and you will get the value of f of 2. Once you get the value of f of 2, you will find one possible value of f of 1. You will similarly get all possible values of f of 1 to get the final value of f of 1, and in the same fashion you will get the value of f of 0 as well finally, right? So this is how the recursion would proceed. Now one thing to note here is there is very high probability of computing the same state again and again. Why? Because you can yourself see that you wanted f of 2 here, you again wanted f of 2 here, and we already see that the tree for f of 2 would be very huge, right? So if you are expanding this tree here, you may not want to expand this f of 2 again here, and to save on that, what you can do, you can simply save the value of f of 2 once it is computed, and next time when someone asks you for f of 2, just return it from your saved array. And that's where this DP array would help. That's the technique which we simply call memoization, right? We just memorize the value which is already computed and use it in the next time, right? So what is the overall time complexity of this entire algorithm? The overall complexity would simply be number of states multiplied by what we are doing inside each of the state, right? So in this particular scenario, number of states would simply be n, because number of distinct value of I and d could be n. Note that you will only call f of I, or you will only compute f of I for every index exactly once, because next time when you want f of I, this condition will be hit, and computing f of I would be considered order 1 operation. So you can avoid that altogether in your complexity. So overall, you will be computing f of I n number of times. When I say computing, basically we are executing this part of the algorithm n number of times. And what is this part of the algorithm doing? We have a loop here which can run up to order n time in worst case, and then we are doing some constant operations, and then we have a function call here which will tell us whether frequency of every element is equal or not. Now this particular function call, there's various way to implement. One possible way would be just iterate over all the frequency and see whether they are equal or not, right? So this will take order c time, where c is the number of characters, right? So the complexity of this entire loop would be n into c. So you are doing order n into c operation n number of times. So overall complexity of this entire algorithm would be n square c, right? Which is sufficient to pass the given time constraint, because n is very small, n is just 1000, and c is only 26, because c only contains lowercase English letters. So overall complexity is simply 26 n square, which is sufficient to pass the given time constraint. So if we have watched this point, I would encourage you to pause and try to code this entire thing by yourself. Next, we will be looking at the code for this particular algorithm, and then we will look at the harder version wherein n is slightly greater, right? So the code is exactly what we discussed. We will simply call, like, this min partitions you can think of this as f. So we want f of 0, right? Now min partition for this would be this, as we discussed, we will simply, if index is n, we'll simply return 0. Otherwise we'll look at our dp array. If it is already calculated, we'll return that. If it is not calculated, we'll calculate. And how to calculate? We'll simply iterate over all the indexes and see if all the frequency of every character is equal so far. Then that's a valid first partition ending at index ind. So sorry, ending at index j. So starting at index ind, ending at index j is a valid partition. So we will simply add one partition for that and partition the remaining array into minimum number of partitions and take minimum across all of them to get our final answer. Now is equal function is also straightforward. What we have done is we have simply, instead of removing non-zero elements, we have simply figured out what is the first non-zero element, and we'll simply compare every element with the first non-zero element. If they are not equal to that, we'll simply return false, otherwise it will be true, which means every element is equals, every non-zero element is equals to the first non-zero element, which in turn means every non-zero elements are equal. That is, frequency of every character is equal, right? So this is the overall algorithm, which is very straightforward. Now let's look at how to optimize this. Now, okay, there is n square c, and if n is 5000, then you can't afford this c here, because this c, n square is something that you can afford, so that's fine, but you can't afford this c here. So either you think of somehow to remove this c, or you think of somehow to remove one of the n from here, right? So let's look at each of these factors. First, n is coming from this ind, that is how many times you are calling this function, or what is your recursive state, right? So it's hard to change the recursive state, because if you change the recursive state, you have to kind of revamp or revise your entire algorithm. So let's not try to remove this n for now. Now in this part, you are doing a inner loop which is going over all the various possible first partition. Again, if you change this loop or remove this loop, your core algorithm will change. So this n is also something you will need. Now this c is something which is needed to figure out whether frequency of every element is equal or not. Now if you can remove this, or if you can compute whether the frequency of every element is equal or not so far in order one time, this c can be removed. So this is the easiest candidate to remove first, or at least try removing first, and if it is not possible, then we look at other candidates, right? So in this case, it is indeed possible to remove c. How? Just think of it. You, like, first of all, you can't call this function, because if you call this function, you need to iterate over every element at least once, or every character at least once, right? So you need to do something smarter, in the sense that you don't want to iterate over every character every time. Instead, you want to compute these things in some fashion, right? And it is very easy to do this. Just forget about what is the problem. Focus on the core problem here. The core problem is, given an array, I need to figure out how many whether or how many distinct frequencies are there in this array. And if the number of distinct frequencies equals to 1, I will execute the statement. If number of distinct frequencies is greater than 1, I will not execute the statement, right? So all you need to do is figure out how many unique frequencies are there, right? I would encourage you to pause and try to think for a moment. I hope you thought about it. You can solve this easily with a map. Now you can either maintain an unordered map that will give you order 1 lookups, or you can do it with a simple array as well. So let's look at one example where we are doing it with an array. The core idea is, we will simply maintain the frequency of what we have seen. So if, let's say, you have seen 1 twice, or let's say you have seen two characters A and B. A has a frequency of 2, B has a frequency of 2. So in this array, you will say there are two characters which have a frequency of 2, right? And when, let's say, you see one more C, or let's say frequency of B is increased to 3, then what you will do, you will simply say one of the character which has frequency of 2 is reduced, one of the characters has now frequency of 3. So in this case, you know that number of distinct element is increased because one of the frequency was 0 previously and this is now become 1, right? So number of distinct element is now increased. So it's all about maintaining the number of distinct elements along with the counters, right? So let's look at one complete example to make this bit more clear. So let's assume that this A is not there at all, right? You are looking at the index starting at 1, and for simplicity what I have done is I have maintained this entire frequency array at every index beforehand. So this is like frequency of A is 0 at this state, frequency of B is 1 at this state, frequency of C is 0, frequency of D is 0 at this state. Now when you do this, you will simply say that, okay, I found one character which has a frequency of 1. So let's get rid of this for now. So you'll say I found one character which has a frequency of 1. Now because previously there was no 1, now there is one extra 1. It means number of distinct element is now equals to 1. Previously there is no element at all which is non-zero. Now there is one element which is non-zero. So you will simply say number of distinct element has increased by 1, right? Now let's move forward. So we got A. Now once we got A, this is how frequency would look like. A and B has occurred one time. So now what is the change? Change is that A occurred one more time. So you will simply say I now have two characters which have frequency of 1. Now will number of distinct element will increase? The answer is no, because this was already non-zero. So we should have already computed the number of distinct element, or 1 as one of the distinct element in this 1, right? So we'll not add one more here because this element was already considered in this count, right? Now let's move forward. Let's say you got B again. So this is how the state would be. So you have changed one of the 1 to 2. So now you are saying that B has 1 previously. So previously B has 1, it means one of the 2 was from B. So you will simply reduce this, right? Now as you reduce this, this is still non-zero. So whatever you have considered for this in this number of distinct element will still stay, right? And you will say I got one new 2. Now notice you got one more non-zero element. Like how to figure out that? Because you can simply look at the previous count and new count, and if the previous count is 0 and new count is 1, it means you just got one new element. So you will simply increase your distinct element count by 1, right? So let's do a couple of more iterations and then we'll look at the code. So we got to 4. Now 4, what has changed? Number of B has increased to 3, right? So again what you will say is there was 1 2, so that got decreased to 0, right? Now because there was 1 2 previously, now there is no 2 at all. It means number of distinct elements should first decrease, right? Now you are saying that we got one new 3 instead of 2. So because there was 0 3 before and now there is just one more 3, number of distinct element will be increased by 1 again, right? So now let's say you got A. So you got 1 from you got new 2 and you have removed 1 from the previous frequency array, right? Previously there was 1 1 1 3. Now you are saying that there is 1 2 1 3, that is 1 was removed and 2 was added. So 1 was removed. If you remove 1, now you are saying that there is no 1 at all. Because there is no 1 at all, it means you just decrease the number of distinct element. Previously there was 1 1 and that's where this distinct element was computing that 1, but now there is no 1, so this distinct element will also need to be reduced. Now you are saying that there is 1 2 instead, so number of distinct element will again increase because there were no 2 previously the count of 2 was 0, now the count of 2 is 1, so number of distinct element has increased. So now there is 1 2, which is basically one new distinct element. So in this same fashion you will keep on updating this this frequency counter and this distinct element simultaneously, and every time we need to understand whether to go in this route or not, you will simply check the value of d. If d is equals to 1, you will go down this route, otherwise you will not do you will not do this, which basically mean whatever exists till I is not a valid first partition. In other words, not the frequency of all the elements from index to I is not equal, right? So in this case as well, if you look at this particular array, frequency of all the element must not be equal because the value of d we got is 2. So you can see frequency of A is actually 2 and frequency of B is actually 3. So the frequency of all the element is not equal, and hence this computation of D was actually indeed correct, right? So with this entire computation we can simply reduce calling this function and simply do some mathematical operation, which is decreasing or increasing d based on whether a new element got introduced or one of the elements got down to 0. So instead of this c, you will be doing one order or few order 1 operations, and this entire complexity would now be reduced from order n square c to order n square, which will be sufficient to pass the constraint for n less than equals to 5000, right? So next we will look at the code. Again, before looking at the code, would encourage you to pause and try to code this entire thing and get it submitted as well. The only reason at this stage to look at the code would be to understand how to code this efficiently, rather than you are not able to code this, because if you are not able to code this, it means you don't understand the solution at this stage. So you should rather rewind and watch the dry run once again to understand that. So the code is exactly what we discussed. This part of the code is exactly similar to the previous part, and even the frequency increment is also same. Now we are now doing two extra things with previous count and current count. Now previous count we will decrement, and now we'll see if after decrementing the value at or number of different previous count is equals to 0 or not. If it is equals to 0, it means previously there was some number which is now not occurring at all, which in turn means number of unique element got decreased by 1. Similarly, for current count you will increment the value, and if current count is equals to 1, which it will signify that there is a number which is now occurring and that hasn't occurred till now, that is number of unique element has increased by 1. So you will simply do unique plus plus. Now if unique is 1, you will simply do this, you will simply consider everything until j as a valid first partition and compute the possible answer for this entire array starting at index I and d. otherwise you will simply continue, right? So hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you're interested, there's one more follow-up which I would encourage you to solve. The follow-up is the space complexity of the entire approach is still order n square. So think about how you can do this entire thing in less than order n square space, right? You can do this entire thing in just order n space as well. Why the space complexity is order n square? Because of this count array. You are maintaining this count array at every iteration, and hence this count array will be in the stack of the recursion, right? So this count array will be persisted in the recursive stack, and hence overall space complexity would be order n square. So we can easily reduce the space complexity from order n square to order n. So try to think of possible approaches to reduce that, and if you need help, we can discuss that in the comment section below. So hope you learn at least one new thing from the video, and I will see you in the next one. Thank you.